All right, should we get started? Okay, some housekeeping before we get in. I mentioned I posted homework 7, so that's on the part 3 page. That should take you about half an hour. If it takes you much longer than half an hour, you might be working too hard on it. Just answer some of the questions at the top, and then there's some coding questions later on. So take a look at that. It's on Gradescope. I wanted to make one comment about the due date for homework 7. If you start working on homework 7 and you have a question that prevents you from moving any further and you want clarification from me, send me an email. If I don't get back to you, you get an automatic extension till after break. I may not have great email service at the end of the week. So if I don't get back to you, that is fair game for you to submit it late. Does that make sense? I don't want you stranded. So that's the homework. Also, the second class for the week is recorded here, so you can just click on that. There are slides here. I didn't post the notebook, but you can create your own. We walked through how to construct it all yourself. Let's see, I think that's everything. This mini exam will be back to you the week we get back from break. So that's sort of the timeline on that. Congrats on the last mini exam. It was the one before this. It was a little bit tougher, but the distribution looks fine to me. If you have any concerns about that, just feel free to reach out. I've had a lot of people come to my office, both with questions, about the class itself, and with struggles with various parts of it. I don't have office hours on Thursday, but I appreciate when folks stop in. So feel free to do that when we get back from break. Any other housekeeping that I've forgotten about? Do you all want to actually use the central limit theorem today? Some enthusiasm I'm looking for. From the rest of you, it's a little meager. All right, so what we did last time was introduce this idea of the distribution of sample means as determined by the central limit theorem. So the big question we tried to answer was, in general, what we see is the sample, but we want to say something about the population that we don't see. So how do we make sense of that? And so we walked through how we use the central limit theorem to get us into the world where we do know something about the distribution. So we talked about what we can do if we knew a distribution. This was a normal distribution, and we can sort of make claims about anything we like, probability-wise, or at least most things we can deal with probabilities. So questions like this. This is only possible if we know the distribution and we know the parameters of the distribution. But in general, we had this idea of we can't observe the entire population, we take samples of it, which introduces some sampling error, which a lot of you are seeing in your homework. In question 3, you're constructing your own sample. So each one of your answers actually will be different on question 3. And that's because we're constructing samples, and there's some sampling error. So you can even rerun your code and get a different number. I know the distribution of your answers, at least what they should be, so I know if you've answered correctly or not, but your answers will not be the same. So the big question we tried to address last time was how do we learn about mu, the population mean, if we don't actually ever observe it? And so we walked through this idea of comparing the population to the sample. So we had a normal distribution, we had the true distribution, and then I took a sample of it, and then we compared the means. And it turns out we essentially always get some sampling error. So here we had a difference of between the truth and the sample mean of 11.5. And our goal was to essentially construct a systematic measure of the closeness of these things. And so we can talk about these distributions in lots of different ways. Last class, we talked about sort of two different perspectives. We walked through an example using die rolls. So this is 5 die rolls with a sample size of 2. So 2 dice, we rolled 5 of them, 5 pairs, and then we took the mean. And so then what we did is we took the means and plotted them on, we ran this like 10,000 times and plotted that histogram of the sample means. With 2 dice, we know the underlying distribution of dice is uniform, 1/6 probability of each side. And we get some sampling error. So this is exactly what you're seeing in question 3. If we just plot the distribution of die rolls, you can confirm that it's essentially a uniform distribution over 6 types, or 6 outcomes. But when we take the sample mean of 2 dice, we get this sort of movement towards the middle. It's this idea where if you roll 2 dice, 2 can only happen if 1 shows up on both dice. So an average of 1 can only happen if you have precisely 2 things happen. 1 has to show up on both dice for the average to be 1. Where there are lots of ways that we can get middle values. Just like there are 6 ways of getting 7 when you roll 2 dice and 1 way of getting 2. So we extended that idea into sample sizes larger than 2. So we have a sample size of 30, which gives us a distribution of the sample means which is much closer to a normal distribution. In fact, I would call this basically normal. And then as we increase the sample size, the outlier events with the samples become very uncommon. The sample means becomes very uncommon. To get an extreme value with a sample mean, we need many extreme values to happen at once, which is much less likely than any one extreme value happening. So we get this movement towards the middle, clumping around the truth. So this is our idea of sample error. Going back to our wait time example, we talked through what would happen. We're waiting for food centered on 12 minutes with a distribution that's known to us. And we plotted the sample means. We took sample sizes of 30. And even here with the sample size of 30, you can see there's variation in the sample mean. We plotted the sample means just like we did with the die rolls. It was much more clustered around the truth. Less variability, less deviation from the truth than the distribution itself, which we plotted in orange. So we get a sort of tightening, just like we do with the die rolls. The intuition applies here as well. So this is the idea with the central limit theorem. It's one of the pieces of magic, one of the sort of most powerful pieces of magic you'll be exposed to in undergrad. It approximates a normal distribution even with a sample size of 30. But then as we increase the sample size, the distribution gets tighter and tighter, clustered around the truth. And this is the one place all semester I will include an emoji in the slides. This is just incredibly powerful. It gives us some extra traction on being able to address questions about the population parameters without ever needing to observe them. Okay, so we had a sample mean, we had a normal distribution, we had a population parameter, mu, we had a normal distribution, and we had a standard error, this sigma over the square root of n. So we have the distribution of the sample means. This is notation for saying that x bar follows this distribution. We also talked about how we don't need to know the underlying distribution. Like with ages in this class, I don't know the distribution of ages that take ECON 0150. But I do know the distribution of the sample mean. No matter what the underlying population looks like, the underlying distribution, whatever that random variable is, it will generate a normal distribution with the sample means. The sample mean will generate a normal distribution that's centered on the truth. So this is a weird looking distribution. It starts off looking like this. And then slowly, as we increase the sample size, we get closer and closer to a normal distribution that's centered on the mean of this distribution, the original distribution. This is part of the magic. So this is where we left off, I believe, last class, right? This was the last one? I'm all out of whack because I recorded the next one in front of us. Okay, so yeah, this is the big ideas with the central limit theorem. We don't need to know the shape of the underlying distribution. We know that the sample means approach the truth with a normal distribution centered on the truth, with a standard error. The standard error is just essentially the standard deviation of the sample means. The standard error is sigma over the square root of n. So this means we can predict the behavior of sample means. If this were not true, our world would look fundamentally different. We wouldn't know so many things. This is how we know stuff based on samples. Okay, so amazing. Any questions here? So I wanted to show you one little simulation of this before we get into the main stuff we're doing today. So I have this little notebook here, and what I'm going to do is actually, so I've constructed a normal distribution, and I have a sample size of 1. What I've done is just construct a sample with sample size 1. So this is just the single observations on their own. So you can see that the underlying distribution looks very normal. There's a YouTube channel called Very Normal that discusses statistics. I've seen someone with the equation for the normal distribution on their shirt. It says IM and then the math for the normal distribution. Yeah, we're very normal in this room. This is, so the underlying distribution here is normal. When we take increasingly large sample sizes, so let's say we go from 1 to 2, we should get a normal distribution as well. So the mean of a normal the distribution of the sample means from an underlying normal distribution is also normal. So you'll notice the bounds here, roughly -2 to 2. If we go to a sample size of 10, that sample mean, the distribution of that sample mean will get much tighter. So we're going to end up with about half the spread. And then if we increase the sample size to 100, we will continue to shrink the distribution. So here it's much less than 1. So we've shrunk the bounds on the main part of the distribution. So as we increase the sample size, we shrink the distribution. But we don't always know the distribution. So what I've done here is I've actually constructed an unknown distribution, which I've defined in the notebook below. So we're going to take a sample from an unknown distribution and see what we find. So I'm going to plot this with a sample size of 1. Does this look normal? No. Maybe uniform, potentially. Give me a guess. If I increase the sample size to 2, what's this going to look like? Yeah, Luke.
It should still be roughly the same. It's not going to be like approximately normal. Yeah.
So maybe not approximately normal. I'm going to maybe say it's not going to look uniform like this. So we will get like a change in the shape, but we will definitely not see normality yet. It's so just like what happens with a 2 dice rolling, we basically get like a pyramid. So it's not quite normal yet, but it's definitely not our original uniform distribution. But if we increase the sample size, so if we go to, let's say, 100, here again, we get a normal distribution. I've said this before, I'll say it again. This is amazing that the normal distribution appears simply by taking sample means. It's not magic, but it's pretty close. So The last thing we're going to do in this notebook, I have a really wonky distribution. So the two examples I have in the slides are uniform and normal, but this one is not. This is, anyone know what this is? This is an exponential distribution. At least that's what it looks like. I'm calling this unknown distribution alt. So what I'm going to do, so we plot a sample size of 1, definitely not normal. We plot a sample size of 2. So it's, the extreme events are less likely, but it's still not very normal. If we go to a sample size of 20, it's maybe getting closer to normal, but it's really not perfectly normal yet. When we go to 200, I would say this is much closer to normal. So as our sample sizes go up, we get closer and closer to a normal distribution, but we're never quite there. And depending on the underlying distribution, like this is a pretty extreme one, it can take us a second. So the sample size, in some cases, needs to be a little bit larger. All right, any questions here? So this is, I think, pretty interesting, just simulating various distributions. I don't know what the underlying distribution is for the ages in this classroom. It looks kind of symmetric, which makes it easier for the central limit theorem to kick in quickly with small samples. But we don't need to know. That's the amazing thing. And we get the normal distribution. Okay, what we're doing today is actually going to try to work with these ideas. So we're going to make some claims about the bounds, sort of the what we call confidence intervals. How many of you have seen confidence intervals before? Yeah, probably almost everyone in this room. If you haven't, that's okay. You might need to put in a little bit of extra work, but that's very okay. So the big question from last time was, what do we do when we don't know the underlying population distribution? What do we know about the distribution of our sample means? The big question for this time is, what do we do with that? So we're going to try to quantify measures of closeness. We're going to essentially systematize how close our sample mean is to the truth. And you'll remember this picture from last time. So we have the distribution of wait times. We took a sample size of 30. We have a standard deviation of 2.5 and then a truth of 12. We had the mean, we had the standard error, which is because we know sigma, we can then talk about the distribution of the sample means. So we know the standard error of the sample means. But if there are alarm bells going off for you about how we use this stuff on this screen, you are on the right track. We don't quite know enough to use our tools yet to quantify the systematic closeness of our sample to the truth. So I want to talk about a few things before we go too deep into this stuff. The first is, why do we have a standard error with the square root of n in the denominator? Did someone just make this up? The answer is no. We discovered this. This is a mathematical result. This is not because we ran a lot of samples and we figured out that it's pretty close to the square root of n. It is exactly the square root of n. So what the standard error does essentially is measure the precision of the estimate. So if we have n independent observations each with a variance of sigma squared, so the standard deviation squared gives us the variance. It turns out the sum of n samples has a variance itself of n to this times the square root of sigma. And the reason this is true, it's sort of technical a bit, but if you've worked with variances, you know this identity. The variance of the sum is equal to the sum of variances. So the variance of a plus b is equal to the variance of a plus the variance of b. So that's true. So the sum of n samples has a variance of sigma squared, n sigma squared. And then to get the average variance, or the variance of the average, we need to divide our sum of variances by n. And it turns out there's another identity here. The n times the variance of a is equal to the variance of n squared times a. So through all of this, because we're dividing by n, we have n to the square sigma squared in the numerator, and then n squared in the denominator. So then one of those n's in the denominator cancels with the n in the numerator, and we just end up with this. So this is the mean variance, or this is the variance of the sample mean, is sigma squared divided by n. But we don't usually deal with the variance, we deal with the standard deviation. So we just take the square root of this thing to get sigma over the square root of n. So this is where the standard error comes from. We're just looking at the standard deviation of a bunch of samples. We know, or a bunch of observations. We know the distribution of the underlying observation. And so we can then just construct the standard error of the sample mean. Any questions here? Bit of a technicality, but it's important to know we're not just throwing that square root of n in arbitrarily. It's there for a very precise reason. So let's say we know what sigma is. We can then just directly calculate probabilities. We've done this so many times, right? We know, if we know the variability in the underlying data, we can then calculate the standard error of the sample mean. So with sigma, we can calculate the standard error. So one question we might ask, what's the probability that x bar is within one standard deviation of the truth? So if we know the variability of x bar by knowing the variability of the distribution, we can answer this question. And the picture looks like this. You've seen this before. We have an underlying distribution, our normal distribution, where we're sampling from a distribution given to us by the central limit theorem. It's going to be centered on the truth. So the errors, the standard errors from the mean, follow a distribution like this. So we've sort of normalized our distribution, and instead of thinking about actual units from the truth, we're thinking about standard deviations from the truth. If you know anything about the t distribution or the t statistic or the z statistic, this is essentially that picture. We'll come back to it later. You don't have to know it, but that's what this picture is. How many standard errors is our observation from the truth? So if we know the distribution, we can just find the area under the curve, and that's exactly what we can do. So we can look at the probability that the difference between our sample and the truth is less than one standard deviation. So that's this thing. And it turns out this is a pretty common question. It's common enough that we often just know this number. It's roughly 68. But we can do this in code. We'll do this in code in a second. If you were to do this in code, how would you start to compute this? I mean, we can take an integral under a normal, but if you've dealt with that integral, it's gross. How would we find this area? Yeah. So essentially what we're doing here is we're looking at the area under the curve, one standard deviation away from the mean, so plus or minus one standard deviation. So that gives us the x variable, right? But we want the area under the curve between those two bounds. So what would we do in that case? What if we use the CDF? So what we're going to do is define the CDF, which gives us the probability up to a particular value. So the CDF gives us the probability we're below 1, and then we subtract off everything that's below -1. So the CDF of 1 minus the CDF of -1, and that would give us this area. Any questions here? Lots of questions. So this is what we call a confidence interval. This is a region where we know for sure 68% of the data will appear. So 68% of the data will be within one standard deviation, or one standard error of the mean. So we would say 68% confident a draw would appear in this part of the data. Okay, this is a confidence interval. Do you all notice anything strange or unusable about this confidence interval? Is this something we can use? I mean, you know the answer is no. So tell me why. Corin. 68, yeah, it's not, it's like maybe not quite as confident as we'd like to be, but there's something even more fundamental than that. This is our confidence interval, right? We're saying 68% of the data falls within this interval. Well, first off, we don't observe mu. We don't even, like if we don't know what the mean is, how do we construct a confidence interval? That's the first question. So as it stands, we cannot use this because we don't observe mu. The other thing, and we'll come back to this a little bit later in class, is we also don't observe sigma. We've been operating on this slide under the assumption that we know sigma, but in practice, you will never see it. So we're gonna have to deal with that question too. So by the end of class today, we're gonna actually have solved those problems, and then we'll construct confidence intervals without even needing to know them. So it turns out the central limit theorem tells us perspective 1, which is one way of thinking about the closeness of x bar and mu, which is because mu is known, it's fixed, there's no variability in the truth, but there is variability in the sample, then we have a distribution of the sample mean around the truth. This is one perspective, and this is the perspective we've been operating under. But there's a mathematically equivalent perspective, which is that we think about the closeness of mu to x bar. So we have a distribution centered around x bar, which tells us how close x bar is to the truth. But remember, this is kind of a weird way of thinking about it because the truth isn't actually random. There's no variability in the truth. But mathematically, these two things are identical. And because they're identical, and because we never see mu, perspective 2 is actually one we can use. So just to convince you a little bit that these two things are actually mathematical, and to give you a bit of visual intuition for how we're going to use the second perspective, I'm going to show you a slide that all of my previous classes have hated. So let's just talk this through. How many of you like this slide at the moment? Okay, just as I suspected. All right, so this first one, we have perspective 1. We're going to center a confidence interval around the truth, and then take 100 samples and check whether the sample falls within the confidence interval. So these are 99% confidence intervals centered on the truth. So the truth is this blue line, and then each one of these is a sample. And for each one of these 100 samples, I've constructed a confidence interval in which is the line. If the sample, which is the dot, if that sample falls close enough to the mean, to the truth, to fall within the 99% confidence interval, I've colored it green. If it falls outside of the confidence interval, I've colored it red. So the first observation is that a 99% confidence interval does not include every sample. In fact, with this picture, we have 1, 2, 3, 4, 5, 6. 6 out of the 100 samples fall outside of our 95% confidence interval. So it's, with this sample of 100, it is 94%. 94% of our data falls within the 95% confidence interval. So we were right on. So the first observation here is that not every sample will fall within the 95% confidence interval of the truth. And this should be expected because samples can be randomly very, very extreme. But this second row is perspective 2. So remember, we can think about the distribution centered on the truth, or we can think about the distribution centered on the sample mean. So changing the center point, we move the 95% confidence interval, the same interval, but now we've centered it on the sample mean. And because the sample mean is actually variable, the confidence interval also moves around. So that's the first observation for perspective 2. The second observation is that every time we miss the confidence interval under perspective 1, we also miss under perspective 2. So with perspective 1, we're saying we're outside the confidence interval when the sample mean falls outside the confidence interval. Under perspective 2, we're saying we miss the confidence interval when the truth is outside of our confidence interval centered on the sample mean. And it turns out these perfectly correspond. The first perspective we cannot work with because we don't observe the truth. That's actually what we're looking for. But with perspective 2, we can actually work with this. Just now the confidence interval will move around following the sample mean. But under this procedure, we will correctly identify a range that contains the truth 95% of the time. In fact, in this example, it was 94% of the time. Okay, any questions here? Okay, after I talked this through, how many of you like this slide? Okay, from 0 to like 1. All right. I love this slide. This is my favorite slide today. Okay, so this is the idea with changing the center point. This bails us out. This is the first of 2 tricks that bail us out of the problem of not knowing the parameters. So this will allow us to construct confidence intervals that are centered on the sample mean and not the truth. I cannot overstate the importance of this idea, even if you hate the slide. Hate's a strong word. Okay, so this, we're going to walk through an example of where we know the standard deviation of the data, but we don't know the center point. We know an X bar, so sample mean. We know the truth, sigma, and we have a sample size of 100. So the first question we're going to ask is, what's the probability that mu, so our truth, is closer than 0.1 to X bar? So it's like we have a distribution and we're thinking about the closeness just in absolute terms. So what we're going to do is actually use some code to construct this. So let's hop over to 3.3. So I'm going to plop in the code, and let's just write out the question in the notebook. Okay, so we need to write out a few things here. So we'll say mu is equal to, well, we don't know what it is. We do know what x bar is. So x bar is equal to 102.3. Our sigma is equal to 1.6. And then our n, our sample size, is equal to 100. So we need to know the standard error. So you'll remember the standard error, Gemini even knows this, unsurprisingly. The standard error is just, as always, sigma divided by the square root of n. So we run this, we put all the parameters in our system. And then what we're going to do is try to figure out the range, the probability that's within 1.1 measure on either side of our x bar. So this is like, we've centered the distribution on x bar, and then we're putting two upper and lower bounds, one upper and one lower bound. I'm going to write this out. We're going to talk about sort of more of what this means in a little bit. But the first thing we're going to do, let's call this upper. So we're going to say upper is equal to the distance, so the measure from the center point, divided by the standard error. So what this is telling us is how many standard errors would we call a spelling mistake a standard error in Econ 0150? No one? All right. Thank you. I consider it a win if one person laughs at a stupid joke. I usually win in this class. So standard errors. How many standard errors is distance? Right, we're looking at how many standard errors away from the mean we're interested in. So if the distance were 1 and the standard error were 1, then we'd be looking at 1 standard error away from the mean. And if the distance were 2 standard errors, and so a distance of 2 and the standard error was 1, we'd be looking at 2 standard standard errors away from the mean. So this is upper. How many standard errors is distance away from the center? And then we can also construct lower, which is the same thing, just negative. Same in the other direction. Okay, so we have upper and lower. And all we're going to do here, just like we always do, we know this is a normal distribution. We want the area up to the upper bound, and then we subtract off the area up to the lower bound. And this gives us the probability that we're within this interval. Okay, nice. Any questions here? So we're going to come back to more examples like this. But this is, you've probably done something like this in your stats class, where you construct like a z-score, and then you compute the z-score with your calculator, and then you consult a z-score table, like in the back of your stats book, open it all up, and like find the probability that corresponds with the z-score you computed on your calculator. This is doing exactly the same thing. It's just you don't need a table. I'm a better door than window. Okay, so this is question 1. So the second question we might ask is sort of the converse, which is what's the 95% confidence interval? So it's asking to get 95% of the data between upper and lower, what do those upper and lower bounds need to be? So anyone know how we do this? I mean, we're going to do this in code. I think the standard way is to check in your, to construct a z-score and then check in your table. But I'm going to do this in code. So we'll put this question 2. So all we have to do actually is construct the standard error, which we've actually already done. And then all we're going to do is consult stats.norm and then get the interval package and just ask it for the 95% confidence interval. Amazing. And then we'll just print off confidence interval. Done. That was quick. Should we call it a day? No. Sorry. We're not going anywhere. So this is the confidence interval, but I want you to think about this for a second. This is the confidence interval around the sample mean. So if we were to rerun this, just like you did in question 3 on your homework, and you get a different x bar. So let's say, x bar was now 101. We would get a different confidence interval. This is a different interval than from before. So if we go back to our original one, this is now different. Every time we resample, this will give us a different confidence interval. What we're saying is not that the truth is in this interval 95% of the time. What we're saying is that following this procedure, 95% of the time, the interval we create will contain the truth. Those are slightly different. 95% of the time following this procedure, the interval we construct will contain the truth. We're not saying 95% of the truth is within this interval. There's no variability with the truth. It's just this procedure generates an interval that will contain the truth 95% of the time. Because fundamentally, the sample is random, which moves the interval around. Okay. It may sound like a subtle distinction, but understanding the process is what allows us to do this stuff in everything we do in inferential statistics. Okay. You may have noticed, and I may have told you already, that one problem is left. I think once we get through this problem, I will send you off to spring break. We just solved the problem by recentering the confidence interval on the truth. On the sample mean. We don't have to know what mu is. We can make confidence intervals without knowing the truth because we can just mathematically move the center of the distribution to be on the sample. So we've solved one of the two problems, but we still don't know what sigma is. You can't just go out and figure sigma. Anyone know what we do here? I know you do. Someone in this room knows. Let's use our best guess. And let's use the sample standard deviation. I'm gonna show you what we do, and then we're gonna talk about some of the nuances. I want you to see the nuances. There's a reason this is a little more complicated than just subbing in S for sigma.
Are we going to be using a t-test or something with this sample?
So we're gonna get to a t-test, yeah. But we're gonna build up some of the intuition before we get there. So Luke is saying, let's use a t-test. And the way we use a t-test is by replacing the truth with our guess. So before we used x bar in place of mu. With sigma, we're going to use the sample equivalent in place of the population equivalent. But I want to show you a picture here. So we're going to use S in place of sigma, but there's a major catch. We're going to get around this problem mathematically. Like, we're not going to make any assumptions. We're going to fully solve this problem. But I want you to see why we can't just simply do this. In your homework, actually, if you were to rerun question 3 a bunch of times, every time you rerun it, I'm asking you for the sample standard deviation. Each time you rerun it, it's going to give you a different sample standard deviation. We actually have a distribution of the sample standard deviation. So this is I've run this 1,000 times. I know what the true standard deviation is. And each time I run a new sample and calculated the sample standard deviation, there's sampling error in that too. So we can't just simply substitute S in for sigma, because not just is there variability in X bar, but there's variability in S. And so substituting something that doesn't change with something that does vary introduces an extra level of variability. And we need to account for that as well. So there's a bunch of fancy math that goes on here. But essentially what happens when we treat the sample standard deviation S as a random variable and then sub it in for the constant sigma, we introduce 2 random variables. One is the sample mean, and the other is the sample standard deviation, which gives us a ratio, essentially, of random variables, which turns out to be a chi-square distribution. But then it turns out the square root of this particular distribution gives us the t distribution, which is very similar to the normal. So there's a lot of math behind the scenes that gets us the t distribution, but it doesn't require us to introduce any new assumptions, except that we have variability in our sample standard deviation. So what we know is that X follows a normal distribution with these things, but then we're introducing S in place of sigma, which gives us the t distribution. So I've plotted 3 distributions here. One of them is the normal, which is in blue. And then I've plotted 2 different t distributions. One is with a degree of freedom of 1. The other is with 5 degrees of freedom. So this is increasing the sample size from 2 to 6. So with very small sample size, we get a t distribution that looks like this in red. But then as we increase the sample size, we go from this red one to the green one, getting us closer to a normal distribution. So the t distribution is a separate distribution than the normal, but as the sample size increases, we get closer and closer to the normal distribution. So in large samples, the t and the normal are very similar, basically identical. And the reason is because the variability of our sample statistics gets smaller and smaller, gets tighter and tighter around the truth, which then means we get closer and closer to a normal distribution of the sample means. Amazing, right? You may laugh, but this is truly amazing. We use this not just in economics, we use this in any field that uses statistics. This is a statistical result. This tells us when we smash atoms together, we don't have to already know what an atom weighs to be able to measure very precisely what the subatomic particles weigh. I'm not a physicist, I don't do those things, but I know they use this. They use these exact same models to measure the weight of subatomic particles. And we use them in economics. So we have this t distribution that we use, and Luke has already mentioned a t-test, which is what we're about to do, which is essentially performing the same types of things we've done with the normal distribution, but on the t distribution. We don't know the true population parameters, but we do know X bar and S. Okay, so let's put it all together. We have X bar following a normal distribution around sigma. We center the distribution on X bar instead of mu. And then with S instead of sigma, we're capturing all of the extra uncertainty in the t distribution. So let's actually run an example here. So we're going to generate some sample wait times and see if we can get some answers to some questions. So we're going to generate a sample. So let's call this example t test. So we'll generate a sample here, and we can just take a look at what this looks like. So huge sample, 30 observations, well, medium-sized sample. And we're going to try to calculate the 95% confidence interval. So this is without knowing what anything fundamental about the underlying distribution is. We can make claims about our level of confidence. This procedure will generate an interval that contains the truth 95% of the time. Okay, so let's get some sample statistics. So we'll just copy this over. So we have x bar, which is the sample mean. We have s, which is the sample standard deviation. We have n, which is the length, and the standard error. So you'll see none of this involves knowing anything about the underlying distribution. We could make this a black box and then not even need to use it. So next, we're actually just going to perform a t-test. We're going to construct a confidence interval. We'll talk about t-tests specifically later, but we're going to use the t statistic or the t distribution to construct critical regions from the t distribution. So the regions that contain 95% of the data. (95% of the data). And another way of saying this is this is well, yeah. So we'll construct this thing, and then we'll talk more about this in a second. But essentially, what this is doing is giving us a value on the t distribution that will allow us to construct a confidence interval. So we have stats. We're looking at the t package. So this is the t distribution. And then PPF is not the production possibility frontier that we know and love from our intro micro class. This is a way of inverting our question. We're just going, it's a stats package you can look at more into. But we're going to ask a region that goes up to the 97.5 percentile. And then we have n minus 1, which is our parameters. So here, this is the critical region. So this is how many standard errors away from the truth, from x bar, will the confidence interval be. So we can multiply this by the standard error to get plus or minus the critical region. But a more direct way of computing this is actually just to construct the confidence interval itself. So the last thing we're going to do is actually, so we have the margin here, which is what we constructed. How many standard errors away from x bar do we need to be to contain 95% of the data? And then we multiply that by the standard error to get the margin. And then we just add and subtract the margin from our x bar, which gives us this interval. A couple of steps, but this will generate for us an interval that contains the truth 95% of the times we run it, but not always. Okay, any questions here? This will generate mistakes for us. 5% of the time, the truth will not be on this interval. The truth is on this interval this time. 12 is the center, and this interval contains 12. Okay, so this is how we construct confidence intervals. I've said a complicated thing. If we took samples, if we took many samples, 95% of them would give us a confidence interval that contained the truth. That's the truth. That's like what this thing is telling us. But the shorthand we often use, which I think is a little confusing, the shorthand we often use is we're 95% confident that the truth is in this interval, even though this is slightly technically incorrect. But that's the words we use to understand, to sort of describe the process. We take many samples, each one will have a different confidence interval, but that process of constructing a confidence interval in this way will generate an interval that contains the truth 95% of the time. That's a mouthful, so we just say we're 95% confident. Okay. Some other questions for you, but I think we're just going to leave it here. Go have a nice break. There's homework due on Friday. Like I said, it shouldn't take you more than half an hour. If you get stuck on something, send me an email, and you get an automatic extension. Go enjoy your break. I'll see you on the other side. Oh, we do not have a mini exam when you get back. Yeah, you too.